Thanks for downloading the In Our Time podcast. For more details about In Our Time and for our terms of use, please go to bbc.co.uk/Radio 4. I hope you enjoy the programme. Hello. In 1740, the Prussian King Frederick the Great wrote, "Philosophers should be the teachers of the world and the teachers of princes. They must think logically, and we must act logically." What it is to think logically has been one of the main concerns of thinkers since the time of the Babylonians. In the 4th century BC, Aristotle turned his attention to the subject and thereby founded the modern discipline of logic. Aristotle's system was used by scholars for over 2,000 years, but in the 19th century was succeeded by something even more powerful and subtle. Today we understand logic as the study of argument and the forms they may take. It's widely used in fields from linguistics to cognitive science, but above all, logic is the vital tool without which computing would never have existed. With me to discuss logic and its uses are A.C. Grayling, Professor of Philosophy at Birkbeck, University of London; Peter Millican, Gilbert Ryle Fellow in Philosophy at Hertford College at the University of Oxford; and Rosanna Keefe, Senior Lecturer in Philosophy at the University of Sheffield. Anthony Grayling, before we get into the history of the subject, can you tell us what you mean by the word logic?
Logic is the science of a valid inference. And by inference I mean drawing conclusions from premises, from assumptions we make or information that we have, and from it we try to deduce or induce a conclusion based on those premises. And what logic does is it tries to understand the best ways of doing that, the valid forms of doing that.
So you're talking about reasoning and you're talking about validity. Can you give us some examples of logical thought?
Well, take a very simple example like this. All men are mortal. Socrates is a man, therefore Socrates is mortal. That's a perfectly standard example of a deduction. From the two premises that all men are mortal and Socrates is a man, you deduce that Socrates is mortal. Now you notice something rather interesting about it. That's a deduction. And if you inspect it closely, you'll see that the conclusion is actually a rearrangement of the information in the premises. So in a way there's no informational novelty there, although there might be psychological novelty because you might not have realized that Socrates is mortal. In the case of an inductive argument, you go beyond the information given in the premises. You say, this one is white, that one is white, the next one is white, so they're all white. And there you're taking a little bit of a risk in your reasoning, but you're going from some samples to a generalization about the whole class. But in the science of logic, traditionally, the focus of attention has been on deduction, that is, on the question, what forms of reasoning are just in virtue of the form, not in virtue of the content of what's said, can you be sure that if you were to put true premises in place, you would be guaranteed a true conclusion.
Where does the word valid, how does the word valid figure in this?
Well, this is very interesting because validity is a purely formal property of an argument. That's to say, it's just about the shape, the structure of the argument, and not what's actually said in it. So, for example, supposing you got a rush of blood to the head and decided to get married, you went off to the local registry office with a vehicle license registration form, hoping that it would serve for a marriage license form. The people would tell you, you've got the wrong form, you've got the wrong set of blanks. You need another set of blanks to be able to fill in the right kind of information for what we're doing. So purely formal matter relates to the validity of arguments. If you put in a true premise or set of premises into a valid form, then you have what's called a sound argument, because the validity of the form plus the truth of the premises will give you a true conclusion. That's a sound argument.
Can you just unravel premises for our listeners who might be worried about this?
Yeah, the premises are the sort of basis, the groundwork, the information, the data, the starting point. There might be information plus some assumptions that you make, and from them you try to draw a conclusion. Drawing a conclusion is called inferring, process of inference. And that's what logic is really interested in. It's in this process of how you can draw inferences from premises, which, providing the form, the shape of the argument is right, will be such that if you've put true statements into the premise slots, you will get a true conclusion.
Peter Millican, we've talked about deductive and inductive. There's also another distinction between formal and informal. Can you tell us how that plays?
Yes, Anthony's already given an example of an argument that is formally valid. All men are mortal, Socrates is a man, therefore Socrates is mortal. Now think of the following argument. All cows are ungulates, Buttercup is a cow, therefore Buttercup is an ungulate. Now, you might not know what ungulate means, but you know that if the premises are true, the first two propositions, then the conclusion, the last one, has to be true as well. That's an example of an argument that's valid in virtue of its form. You don't need to know the meaning of the terms. As long as they're slotted in correctly into the form, you know that you'll only get from truths to truth. Now, informal logic is concerned with other kinds of good and bad reasoning, for example, vagueness, ambiguity, appeals to authority, circular arguments, the kinds of fallacies that we can make in informal reasoning.
Such as?
Well, an example would be circular reasoning, where you end up taking for granted the point at issue. So, for example, suppose I want to prove that everything has a cause, and I say, well, anything that didn't have a cause would have to cause itself, and that's impossible. Actually, I'm arguing in a circle because I'm taking for granted that something which isn't caused by something else has to have itself as a cause. I'm taking for granted that everything has a cause in putting forward my argument.
Is there a chasm, as more than a distinction, between formal and informal logic? Is it a big distinction here?
Well, yes, it is. I mean, in the sense that with a formal argument, the idea is that you can pin it down pretty precisely. You can say, here is a form of argument where if you put the right things in the slots... As
Anthony was saying about the marriage certificate. Aptly chosen.
So, if you put the various predicates in the right place consistently, as you're meant to, then you're guaranteed, if you've got true premises, to get to a true conclusion.
But informal and logical, they don't quite seem to rest together as two words. Do you have problems with that? Not you. I do, but I mean not you. Are there problems with that?
Well, not really, because I think here we're saying that informal is being used as a contrast with formal. So we've got a very clear understanding of what formal logic is. But then we're aware that reasoning in ordinary life can go wrong in all sorts of ways. And we simply take all those various things that can go wrong. It's a bit of a rag bag, but put them under the heading of informal logic.
In the introduction, I talked about that Aristotle, they seem to be talking about logic in Babylonian times, from what you know, and I now know. But Aristotle began to write about it and give it space, and it carried through for hundreds of years. What was the nature of his contribution? What was the key? Was there a key to his contribution, and what was that?
Well, Aristotle was concerned particularly with arguments which we call syllogisms.
Which are?
Well, start from the notion of a categorical proposition, and a categorical proposition is one that concerns a subject and a predicate. So, for example, all cows eat grass. So cows is the subject, eating grass is the predicate. And there are four different types of categorical propositions. Broadly, they take the form: every F is G, no F is G, some F is G, some F is not G. So you put something in place of F and G, cows and eating grass or whatever it might be, and you've got four different kinds of proposition. Now, what Aristotle did was look at arguments that connect two of those kinds of proposition with a third one. It's easiest to understand it by example. So, for example, all mammals are animals, all humans are mammals, therefore all humans are animals. And that is a valid syllogism. From the first two propositions, the third one follows. Another one, very different kind, is no cows have wings, some mammals are cows, therefore some mammals do not have wings. That's another valid form of syllogism. And what Aristotle did, essentially, was look through all the different kinds of arguments that you could have of this type and categorise them and tell us which are good and which aren't.
And you found, reading from my notes, 256, of which only 19 were valid.
Yes, the exact number that one counts as valid is potentially controversial depending on various things, but essentially you've got 4 different types of proposition. You can put them in different orders, and so you end up with 256.
Very briefly, Peter, people listening would say all animals are primates, that's what Socrates is. But quite simple, it seems. Now, why was this such a hard driver of philosophy? Why did it drive it so strongly, this idea of the syllogism?
Well, I think it's a very attractive idea to philosophers. I mean, philosophers naturally like system. They like to understand why things work at a deep level, and we're all concerned with reasoning and logic. So I think it's understandable that it would have captured the fascination.
Rosanna Keefe, can you take that on? What was he able to do, Aristotle, with his invention of the syllogism?
Well, what's particularly important and impressive about his system is the systematicity of it and the generality of it. He was able to give rules and methods to show that some particular form of syllogism was valid or was not valid, and he was able to give some general results about his system. So it was more than just taxonomic exercise. It was a very full system. So, for example, his rules for showing that a particular argument form were valid involved some rules of conversion, he called. So, for example, from some A is a B, you can conclude some B's are A. If some of my pets are furry, some furry things are my pets. And other rules like that. And then he could show that any valid syllogism could be reduced or explained in terms of 2 fundamental ones that he thought were obviously valid. So one of those is one that Peter gave an example of.
Socrates.
All humans are mammals, all
right.
Mammals are animals, therefore all humans are animals. That gets called Barbara. And the other one is celerant, which is an example of which is no dog's a robot, all poodles are dogs, therefore no poodles are robots. So those were, he thought, obviously valid, and then he could show why other forms were valid by using those and his other rules.
Was this these syllogisms, these 3-liners, as it were? I know I'm treading on oceans, really, but still, they do seem quite simple, and yet they had such a big impact. Can you tell me why this way of Aristotle bringing this together in such a neat, almost haiku way, drove philosophy for so long, and still, to a certain extent, it was the recent take-up was from his basis? What is it about that which organises reasoning in a way which validates that method for hundreds of years to come?
I think it's partly the level of abstraction with which he could deal with it. So all sorts of arguments can be of these various forms, and some of them aren't so obviously valid as the ones that we've been talking about. And he had methods of showing that they were nonetheless valid. And then his hope was that reasoning would follow these forms. So, for example, his account of scientific knowledge required demonstrations that had to start from necessarily true premises that were better known than the conclusion, and which ideally should follow the form of a syllogism. So he felt that it was the foundation of science.
That's interesting. From the very beginning, he switched the idea into science, didn't he? Because that was his primary concern, if he had a primary concern, knowing so much about so much. But he switched it into science. There was another group of Greek philosophers examining a different type of logical argument. I'm afraid I must use this terrible broadcasting word briefly. Can you tell us what the Stoics were interested in?
Yes, they were interested in the logic of different bits of language. So they were interested in or and if then, and how those logical connectives work, what rules govern them.
For instance?
So yes, they had talked about 5 indemonstrable rules, which again should seem compelling. So one of them, modus ponens, here's an example: if it's raining, it's cloudy. It's raining, therefore it's cloudy. Another one is if it's not both Lydia's birthday and Miranda's birthday. It is Lydia's birthday, so it's not Miranda's birthday. It's a general form of argument that's always valid, whatever you put in. So they'd express that in general terms. So in that last case, they'd express it as not both the first and the second, the first, so not the second. And whatever sentence you put in for the first or the second, you get out a valid argument. And they hope to show that all sorts of arguments were valid using these basic ones.
Thank you very much. Anthony Grayling, can you tell us how this... We've got some idea. It's already complicated, it seems simple. That's the fascination, isn't it? I mean, you've already complicated it, but it seems to start from simple premises. Why, I'm asking you the same question, why did it persist for so long? Why was it taken up by so many inordinately intelligent people for sentences? We're going to go right from the 4th century BC to the Middle Ages, where you had great thinkers. They were thinking in the context of religion, let us say, but they picked up his logic, as did the Islamic scholars before them. Let's talk about the Middle Ages. What was the attraction? What was the drive?
Well, first let's just say that the point about all this is that even though the examples we've been talking about here are very simple examples, there seem to be a lot of sort of poodling and animalistic trivialities. In fact, they do tell us a great deal, because they firstly constitute an instrument which helps us to think more powerfully and to govern our reasoning much more powerfully. But also, of course, they can be generalized. There's a great deal, for example, of mileage in understanding these things. What the Stoic logicians were concerned with, and a great deal of what the Stoics wrote and devised in antiquity, was lost for quite a long time, which was why the Aristotelian logic kind of survived and then got rediscovered, large parts of it in medieval times, so that the schoolmen, as they're called, of the medieval era, in the absence of telly and bingo in those long winter evenings, were able to devote their attention to trying to explore and spell out many more of the implications. So Rosanna's just been talking about the interest that the Stoics had in words like and, if, not, and so on. These are known as syncategorematic terms. That is, they're ones that don't denote anything out there in the world, but they have functions within sentences, functions within propositions, because they combine terms in the propositions in different ways. So that an example is that if you use the word and you join two propositions, let's call them P and Q, then you know that the complex proposition P and Q can only be true if both P is true and Q is true. Whereas in the case of a disjunctive proposition, P or Q, only one of them has to be true for the whole thing to be true. And these are very consequential things to recognize, even though they seem very simple, because once you start to build up a much larger structure of reasoning from these simple things, it really provides a handrail through the argument. Imagine some very, very complex chain of reasoning where you're thinking about some really rather fascinating subject matter. Well, you would have available to you this instrument. Indeed, Aristotle's logic had been called the organon, or the instrument, as a kind of help or aid to reasoning, and it would help to steer you through something which might be very complicated in its own right. So it's a powerful tool, and that's why it retained the fascination of thinkers who wanted to explore it in more depth and understand much more about the way that really good reasoning works.
But why were the medieval schoolmen so attracted to it, and they developed it and multiplied it? Peter Millican.
Well, one of their interests was actually in things that went beyond Aristotle. I mean, they were particularly interested in certain types of inference that might superficially seem valid, but in fact aren't. So suppose I give you an example. I know that she's in London or Oxford, but it doesn't actually follow that I know she's in London or that I know she's in Oxford. So here we have a case where what might seem to follow doesn't. And that's the kind of case that many of the medievals, particularly in the 14th century, were investigating. They were looking at cases where a simple-minded application of logic didn't work, and they were looking to try to understand the logic of terms like knowledge and belief and so forth.
So let's take that. I know that she's in London or Oxford. How would they push that?
Well, unfortunately, in the 14th century, you don't have a single systematic theory. You've got a lot of people doing their thing in different places, people like William of Ockham and Thomas Bradwardine and Gregory of Rimini and John Buridan. And we don't have a sort of organised theory there. Typically what we've got is different thinkers pointing out the occurrence of various cases like this and drawing them to the attention of other philosophers.
But they explored this, and then quite soon after that Aristotle went out of favour, didn't he?
Yes, he went right out of favour. That can be traced to thinkers like Francis Bacon and Descartes and John Locke. Their criticism of it was that logic was sterile. They thought that the kinds of things that Aristotle was looking at, those arguments, were pretty trivial. They didn't give any real insight because they were so obvious. And what these philosophers were concerned with was more discovery of good arguments. So if you think, for example, of a geometrical proof, you start from certain assumptions, you have to find your way towards some conclusion. And typically the way you do that is by some ingenious construction. You draw in certain lines, put in various angles, and then you find some clever way of connecting the premises, what you took for granted, with the conclusion, which is what you want to get to. And partly based on this sort of model, the early modern thinkers looked at Aristotle and said, well, it's useless for that. Syllogism may be good for setting out arguments once you've discovered them, but what we're really interested in is finding good arguments, finding the links between ideas that enable us to derive new knowledge. So after Locke, the understanding of logic, what logic becomes thought of as, is more a study of our ideas and the study of our cognitive faculties.
Anthony.
Yes, I mean, the interesting thing there, I think, is that the 17th century, of course, 16th and 17th century is the rise of modern science, and people like Bacon were very interested in how you do science, so what kind of methodology would get you to more empirical results. And it looked as though the Aristotelian syllogistic, which is specifically about forms of deductive reasoning, were much less used to you than, for example, kinds of inductive reasoning, ways of accumulating observations, for example, and superinducing theory onto them.
Bacon's idea of observational experimental science, which led to the Royal Society.
Yes, indeed. So you get a shift, if you like, of emphasis from logic as a study of valid forms of deductive reasoning to a more general conception of logic as a science of inquiry.
So it seemed, Rosanna Keefe, that logic was out for a while. Maybe still existed among some schoolmen who refused not to be schoolmen for 2 or 3 centuries, but Locke and Hume and Descartes were saying it's not the way to go. In fact, they were quite snooty about it. Yet, in the 19th century, I suppose unexpectedly, in this dramatic story of the development of logic, it was reborn, and one of the important figures was a British mathematician called George Boole. What did he do that made it important again?
Well, one of the things he wanted was an abstract system that, as he said, showed that the laws of thought were as rigorous as the laws of mathematics. And he wanted a system, something like Aristotle's, only more powerful. And one thing he did was notice the similarity between algebra and logical laws. For example, the similarity between and multiplication, and between or and addition.
That's interesting, isn't it?
Yes. So a simple example, A or B is the same as B or A, just as X plus Y is the same as Y plus X, and then all sorts of more complex similarities. So what he did was come up with a system of algebraic laws that he took to govern logic, and he could use those to assess arguments, show arguments to be valid. One of the interpretations of his system has these algebraic laws to which you can only put values 0 and 1. And if you think of 0 as corresponding to falsity and 1 to truth, then you get a propositional logic, the kind of thing that the Stoics were looking for.
Was this the first time logic and mathematics had been conjoined in that way?
Well, I think Leibniz also wanted something similar. He recognised similarities between algebra and logic too. So not altogether, no. And around the same time, there are other mathematicians who are interested in the same sorts of relations. So supposedly De Morgan published an important book on logic on the very same day that Boole published his the mathematical analysis of logic in 1847. So it was in the air, I think.
Why do you think it was? Oh, sorry, Peter.
So I was just going to say, it would give a wrong impression to suppose that in the early modern period the desire for logic in the formal sense completely disappeared. And I think Leibniz has already been mentioned. I think we can also mention Thomas Hobbes. Hobbes said that thinking is basically calculation, and Leibniz took this further and was looking for what he called a universal characteristic or a universal logical language. And the idea was a language within which reasoning could be, as it were, computed. So he, to some extent, inspired Frege, who mentions him. And there were various people like William Stanley Jevons took Boolean ideas and actually built a logic machine in which this idea of computing things came to reality. You can see it in the Museum of the History of Science at Oxford.
Steve, Anthony, Peter's mentioned Frege. He is the man who supposedly revolutionises logic completely. Maybe that's too big a claim. Can you tell us about Frege and why he matters?
Yes, certainly. He's a very, very significant figure in
dates.
Yes, but it's relevant in talking about Frege, just to follow on from Peter's point there about the way that logic and the sort of Aristotelian kind of canon remained of some significance. Kant, for example, in the late 18th century, the great Immanuel Kant thought that the Aristotelian-based logic was a completed science, and he made great use of it in constructing his theory in the Critique of Pure Reason. But it was this move in people like George Boole and Augustus de Morgan and Jevons and others who were starting to use algebra to try to express some of these fundamental logical ideas that gave Frege in part gave him his clue. I mean, for example, Augustus de Morgan recognized that what had always been thought of as laws of thought, which seemed to be a sort of rather psychological way of thinking about logic, and these laws of thought were principle of identity, which says A is A, or X is X, if you like, principle of the law of excluded middle, which says you can't have both X and not X, that's the principle of non-contradiction, and excluded middle, which says either you have X or you have not X. That in fact the last two, if you put them into an algebraic form, you see that they are just versions of the same thing. So already this way of symbolizing, of using mathematical techniques to express some of these logical ideas was beginning to show that there is a possible increase of power in our understanding of those logical notions. And this is what Frege capitalized on. Frege's innovations...
This is the late 19th century.
In the very late 19th century,
Yeah.
yes. Frege's work showed that the traditional logic, the Aristotle-based logic, was actually just a small part of logic, really. And what Frege had done was to show that you could massively generalize insights into logic, a much, much wider field of application. And he did this in a number of rather complicated ways, but one illustration of how he did it was this. If you take a very simple relational proposition like, say, Jack loves Jill, let's say, in the Aristotelian logic, when a term occurs as a subject of a proposition, it works in a very different way from the way that a term works when it occurs in the predicate of the proposition. So on Aristotle's analysis, Jack loves Jill gives us Jack as the subject and loves Jill as the predicate. But what Frege was able to do by really sort of rather brilliant but simple insights into how you formalize this, how you symbolize it, to show that Jack and Jill can operate on the same logical level, and that you can have what we would call a two-place predicate, that is, loves, which applies to both of them because they stand in that relation to one another. So you can write it as predicate expression loves and then Jack Jill. And but just by this kind of technique and by the development of what he called a concept script, a Begriffsschrift, you could formalize, symbolize all these relations and show how inferences work in them. And this was like the development of a machine which produced massively more sausages than the Aristotle machine did.
Rosanna, can you? This is part of a larger, grander project in Frege's system called logicism. What did he mean by that?
The idea of logicism was that arithmetic can be reduced to logic. So we can conjure up all of arithmetic from logical foundations. And this was important because the idea was to give secure foundations to mathematics. So rather than resting on axioms that you might just think were intuitively true, or trying to base maths on something empirical, we can base it on logical foundations. So, for example, you can understand a sentence with the number 1 in purely logical terms. So if I say there's one dog, exactly one dog, that gets translated logically as there's something with X, which is a dog, and anything that's a dog is that X. So it's a logical formula that gives you an understanding of number, and from that you can build up to understanding of number and more complex and rational numbers, etc.
Peter Millican, I see you wanted to get in, but when you get in, can you also tell us why a letter from the British philosopher Bertrand Russell influenced Frege so heavily, and what was the solution to the problem that Russell identified?
Right, yes. First of all, I was just going to say something that Rosanna's mentioned there is pretty crucial in Frege's thought, the introduction of variables x's and y's. So where if you take something like all cows eat grass, for Frege this is interpreted as for all x, if x is a cow, then x eats grass.
What does that do that helps?
Well, what it does, it enables the all and some propositions that Aristotle had dealt with to be incorporated within a much larger system. And as Anthony was saying, you can actually build up propositions of arbitrary complexity by putting brackets within brackets with these quantifiers and variables in such a way that you get a much, much more general system. You can express, well, at least Frege wanted to express all the truths of mathematics. Now, what Bertrand Russell pointed out, unfortunately, is that a particular proposition that can be expressed within Frege's logic turns out to produce a contradiction. And he wrote in 1902 to Frege saying, here's this contradiction I've found. And clearly, if what you're trying to do is to build mathematics on the foundation of logic, the last thing you want to find is a contradiction in your system of logic.
Briefly, Anthony, what was the contradiction and what was Frege's response to it?
Well, the contradiction is this. Russell was trying to define number in terms of classes of things. So you try to define, say, the number naught by saying that naught is the class of all those classes which are empty, which have no members. And the number 1 is the class of all those classes that have just a single member. Number 2, class of all those classes that have doubleton members, and so on. So it looks as though you're reasoning circularly here, but actually you're not using the notion of number to try and define number in that way. So crucially, you're making use of the idea of a class. And then it turns out that you get this difficulty. Some classes are members of the class of classes, okay, but some classes or class of teaspoons are not themselves teaspoons. So you can ask yourself the following question: what can one say about the class of all those classes that are not members of themselves? Would it be a member of itself if it weren't? Answer yes. And can it be a member of itself if it isn't a member of itself? Answer yes. So you've got a contradiction. Now, a way of trying to illustrate this is not an exact parallel, so do be careful not making it exact parallel. But supposing you have a barber in a village who shaves all and only the men who shave themselves. Does he shave himself or not? If he does, then he doesn't. And if he doesn't, then he does. So it's in a way a rather similar illustration of what the difficulty was here. If this idea of classes can generate a paradox in that way, then you can't use it to try to define the basic notions of arithmetic. And remember that arithmetic can take translations from all the other branches of mathematics. So this is very, very fundamental. Russell's solution was to say, well, somewhat arbitrarily, I'm not going to allow classes of one type to take as members other classes of the same type. So you've got to have a kind of hierarchy of kinds of class, and the higher levels of the hierarchy can take as members of the lower levels, but they can't take members at the same level. So you avoid the sort of problem you get when you say, what I am now saying is false, because if it is false, then it's true, and if it's true that it's false, then etc., etc. And you get into that kind of muddle. To avoid it, you have to introduce this rather ad hoc manoeuvre of inventing a hierarchy.
As I understand it, Rosanna Keefe, Frege introduced this as an appendix to his last work, and that was his last work on this subject. He thought that the paradox, as it were, it stopped him in his tracks in some way, yet his influence on the scope of philosophy went on very powerfully. Can you just give us an outline of how he influenced the field of philosophy in the 20th century?
Yes. In fact, he wasn't that widely read initially. He did directly influence Russell and Wittgenstein and Carnap, which is obviously important influences. But certainly in the last 50 years, he is one of the most seen as one of the most important influential philosophers. Number of reasons for that. One, his logical system allows us to formulate theses much more rigorously. We can make these subtle distinctions, and that is used across all sorts of areas of philosophy. Another thing is his conception of logic, whereas, as has been mentioned, some of his predecessors saw logic as really a part of psychology. It was interested in how we think, laws of actual thinking. Frege was very opposed to that psychologism and wanted to take logic as autonomous. There are laws of logic that apply even if people didn't reason by them, they would apply. And that conception of logic is very widely held today. Other aspects of his influence relate to his work in the philosophy of language, which is closely tied in with his work in logic.
Peter Millican, we did a program on imaginary numbers a few weeks ago, and we were talking there about abstract thought going on among persons who wanted to think about imaginary numbers for centuries, and then it turned out to have an extraordinary practical application which actually helped to make the world in which we live, helped in a big way. Something the same seems to happen here, doesn't it? We're into... Hobbes mentioned computation, I think, or calculation.
That's right. Yeah.
Yes, and now the logic makes its entrance here. Can we use Alan Turing as an example of how that happened?
Yes, it's actually a beautiful example. There was a lot of thinking going on in the early 20th century about the foundations of mathematics. We've already touched on that with Frege and Russell and their logicist enterprise. And one of the big puzzles in the 1930s was whether it's possible to produce a decision procedure whereby you can find out with absolute certainty whether a particular set of axioms and rules will or will not give you a proof of a particular formula. So one's trying to find out the limits of what can be demonstrated. Now, Alan Turing, in order to investigate this question, came up with a very simple model of what a computer might be, called a Turing machine. It has certain very well-defined operations that limit what it can do. He showed that it can do wonderful things. All sorts of things that we intuitively think of as computable are computable by a Turing machine. But then he showed that there are some things that cannot be computed, even in principle, by such a machine. Now, what then happened much, much later is that people looked at this and said, oh, here is a model for a universal computer. Here is a theory which can provide the basis for a lot of computer science. And the Turing machine is still discussed in those terms today.
And Anthony, are there other? Shall we stick with this, the idea of the practicalities, because we haven't got much time left, and it is interesting. Can you tell us what other, as it were, practical developments have come from these centuries of thinking?
Well, firstly, Rosanna mentioned earlier Boole and Boole's ones and zeros in his algebra. This is really kind of digitization of thinking about how you might have a calculating device or a computing device early on. Turing's machine wasn't a machine. It didn't have any cogs and wheels and smoke coming out of it. It was actually a piece of paper with some pencil marks on it. And these ideas fed into the possibility that we now all take for granted. The mobile telephones that we've got switched off in our pockets here have got more computing power than the Apollo rocket that went to the moon back in 1969. And all this is a direct outcome of a great deal of the work that went into logic and the foundations of mathematics. Very, very quickly coming to be applied. It looks very abstract. When we were talking earlier about Aristotelian syllogistic, it seemed very simple, it seemed very abstract and remote from ordinary thinking and applications. But here is a wonderful example of how it feeds into that. Also, however, into our understanding of maybe even of neuropsychology, let's say, because if it's true that the brain is a neural network and functions in a sort of parallel processing kind of way, then this is something which is added on to our understanding of the world and important features of it, which use these ideas, very fundamental ideas, from logic.
Peter Millican.
Yeah, one point that's perhaps worth making here is what a difference the computer makes. Aristotelian logic was criticised very much in the early modern period for being so trivial. But what the computer can do is take millions and billions of trivial operations and make something interesting from them. So, for example, everything that goes on in a chess computer, each little operation is tiny and trivial. String them all together and you get a grandmaster. So the computer has really brought logic to fruition. It enables what seem to be trivial rules to be combined in remarkably fruitful ways in almost every field of human endeavour.
And takes us into artificial intelligence.
Oh, absolutely, yes. Artificial intelligence is based a lot on logic. You get developments of logic to handle new things, to represent knowledge, inferential relationships, cause-effect, spatial events, and so on, probability and uncertainty. It's very much growing in that field.
Well, thank you all very much. Thank you, Rosanna Keefe, Anthony Grayling, Peter Millican. And next week we'll be talking about the unicorn. Thanks for listening.
If you've enjoyed this Radio 4 podcast, why not try others, such as Thinking Aloud, where Laurie Taylor discusses the latest social science research. To find out more, visit bbc.co.uk/Radio 4.